Hi, it's Dr. Robin, aka Double O Pi. In this short video, I'm going to talk about the sorts of concentration units we use for very dilute solutions. When we talk about concentrations in general chemistry, a lot of the time we use units of molarity, moles per liter. You might also recognize some other concentration units you've learned about, like mole fraction, molality, and mass percent. If you don't remember those units, I'll drop a link to my concentration unit video in the description below. These units are best used for fairly concentrated solutions. What if you're dealing with a more dilute solution? For example, let's say that you have a solution of HCl and you measure its pH as 4.8. If you do the math, you'll realize that the concentration of HCl in this solution is 10 to the minus 4.8. In other words, 1.6 times 10 to the minus 5th molar. That's kind of awkward to talk about. So when dealing with dilute solutions, scientists tend to use one of two classes of concentration units. The first type of units are related to molarity, and the second type is related to mass percent. We are going to start with the molarity-related units because they're the easiest to remember. Basically, we're going to use metric prefixes to create smaller units of measure. Millimolar would be 1/1000th of a molar. You can use the equivalents 1000 millimolar equals 1 molar in your unit conversions. Micromolar would be 1/1,000,000th of a molar, so use the equivalents 1,000,000 micromolar equals 1 molar to convert. Let's go back to the dilute solution of HCl that I was talking about earlier. 1.6 times 10 to the minus 5th molar can be converted to give 1.6 times 10 to the minus 2 millimolar, or 0.016 millimolar. That's still a bit awkward, so let's convert that concentration into micromolar instead. This time we end up with a 16 micromolar solution. That's a lot easier to both say and write. So what if your solution is so dilute that even micromolar isn't small enough? Well, you just keep rolling with those metric prefixes. Nanomolar would be 1/1000th of a molar, 10 to the 9th nanomolar equals 1 molar. Picomolar would be 1/1,000,000th of 1 molar, 10 to the 12th picomolar equals 1 molar. At this point, you might be thinking, Dr. Robin, there's no way anyone could possibly measure anything at the nanomolar or picomolar level. I promise you, you can. Almost all of the measurements I did for my doctoral research were nanomolar concentrations, and my lab mate Kelly was measuring a different analyte at picomolar concentrations. As I said, the molarity-related units are usually the easiest for people to grasp conceptually, and this makes sense. Most people who have taken chemistry understand molarity, and they definitely understand metric prefixes. But in my experience, those actually aren't the most used units for dilute solutions. What you're most likely to see are the family of mass percent related units. As a review, to find mass percent, you take the mass of your analyte and divide by the total mass, often the mass of your solution, though this unit also can be used for solids or gases. Then you multiply by 100%. Let's take a little break here and think about the origins of the word percent. This comes from the Latin percentum, or each hundred. Basically, if you break something into 100 parts, how many of those parts will be the thing you're interested in? For dilute solutions, we're going to do something similar, but instead of looking at hundredths, we're going to look at smaller and smaller fractions. Some people talk about parts per thousand or per mil, often abbreviated with this symbol, but that is relatively uncommon. It's more understandable and not all that difficult to call something 0.1% instead of 1 part per mil or 1 part per thousand. However, if you have something that's very small, you're likely to see concentrations expressed as parts per million, abbreviated ppm, or parts per billion, which is abbreviated as ppb. You might even find concentrations in parts per trillion, or ppt. So what do these units mean? Let's say that we have 1 part per million of our analyte. That means that if we split the total into 1 million parts, only one of those would be the chemical we care about. Let's translate that into actual measurement terms. If you had 1 million grams of some mixture, only 1 gram of that mixture would be your analyte. But that's not a practical illustration. 1 million grams is 1,000 kilograms, or a metric ton, and most people can't envision that. So let's scale down a bit. What if you had 1,000 grams, 1 kilogram? 1/1,000,000th of a kilogram is 1,000 grams divided by a million, or 0.001 gram, 1 milligram. So one way you can think of a part per million is 1 milligram per kilogram. If you're dealing with aqueous solutions, remember that a liter of water weighs 1 kilogram. So another way you can think of a part per million is 1 milligram per liter. You'll see all of these units, parts per million, milligrams per kilogram, and milligrams per liter, in the scientific literature, and they all mean the same thing. Now that we've talked a bit about parts per million, let's talk about the more dilute concentration units in this family. 1 part per billion means 1 gram in a billion grams. But again, it's a bit hard to wrap your head around a billion grams. If we think about a kilogram again, we can do the math and see that this works out to 1 microgram per kilogram. For aqueous solutions, that's 1 microgram per liter. Along the same lines, 1 part per trillion would be 1 nanogram per kilogram, or 1 nanogram per liter. Let's now use these units to do a real-life comparison. Many of you may have heard that almost 10 years ago, unsafe levels of lead were discovered in Flint, Michigan. But what does it mean to have unsafe levels of lead? According to the Environmental Protection Agency, or EPA, the acceptable maximum contaminant level for lead is 15 parts per billion, 15 micrograms per liter. The measured lead concentrations in Flint varied by location, but some of the drinking water samples that they tested had lead concentrations over 100 parts per million. That's 100 milligrams per liter, or 100,000 micrograms per liter. So there was more than 6,000 times more lead than you would find in safe drinking water. This has been a brief overview of concentration units that we use for dilute solutions. I personally learned about these units while doing research in environmental chemistry, but once I became familiar with them, I started seeing them everywhere, like in the annual water quality reports I get from my local utility company. I hope this has been helpful, and I look forward to seeing you again soon.